My name's Tim Evans, and I work out of Power Services San Antonio office. This is Chris Larson. He's our manager out of the San Antonio office, and is usually the guy that calls on you guys, but I'm down here a lot, so I pop in and out often too. If you aren't aware of Power Services, we are a rotating equipment distributor, so pumps, compressors, that kind of stuff, and then also a fabricator, so we build stuff like vessels, heater treaters, black units, different stuff like that that you guys use, and we've sold Marathon a lot of stuff historically and built a lot of stuff for you guys. But today we're going to do a centrifugal pump training for you guys, and we do this a few different ways, and I'll kind of ask you guys what you're looking for and what you guys want to get out of it, and we'll kind of tailor it to what you guys want. This is the tool we're going to be using, and it's an acrylic ANSI pump. ANSI pump, just a American National Standards Institute, just like a lot of your guys' pumps out there, except it's, you know, obviously clear, probably smaller than a lot of the ones you guys use, and pumping water instead of oil or condensate or salt water, but otherwise the same. And we can do a lot of stuff with this pump and train a lot of different things. We can do like centrifugal pump principles and why centrifugal pumps work, why you want to use one in this situation versus this situation. We can use them to do curves and talk about curves and build different pump curves in case you guys don't have them. Helps understand curves, and we'll certainly get into that just so we're all making sure we're speaking the same language when we go through this training. And then the third thing we do a lot with this pump, which is probably what we'll focus on mostly today, or try to, because I think that's what you guys will get the most benefit out of, is kind of troubleshooting pump problems. Okay, so when we're out there operating and the pump sounds like it's pumping rocks and it's not producing enough pressure, or it's too low flow, or it's too high flow, we need to back it down. Whatever some of those problems might be, we're going to talk about how to address them here and what some of those problems do inside the pump, so we can kind of demonstrate that and what we get into. And I'm assuming that would probably be the most beneficial thing for you guys. Is that kind of where you guys want to go with this? Sure. Probably helpful? Okay. And we'll cover on a little bit of all of that just by going through it. But, okay, we've got the temperature probe. Put that up too. So, just so we're all starting the same language, we'll start by going through this pump, what some of the components are, parts and pieces, and then we'll come over and we'll start talking about curves a little bit, again, to make sure all of our terminology is the same and we're all thinking the same direction, okay? So like I said, this is a centrifugal ANSI overhung single stage pump, okay? Overhung just because the impeller is overhung beyond the bearings, okay? There's no other bearing set over here where it's in between the bearings, okay? ANSI pump, just American National Standards Institute, they have standards on sizing, performance, and a lot of the other things about these pumps. And we can get into that more if you guys want, but I don't think this is exactly the class to do that right now. But just to say, ANSI pumps have a lot of interchangeability in parts, sizing, and performance, so they're really common, really good price for what you get out of an ANSI pump, and that's why we see most of them in our industry out there in the oil field. So what we're looking at is we just have a pump motor here, and we've got a horsepower monitor here so we can see what horsepower we're actually drawing with the motor. Coupling guard, coupling inside. This is our power frame for our pump, and that's going to be a ANSI rated, so it fits ANSI dimensions and ANSI standards. Behind that, or in front of that I should say, you can see our shaft here, and then we've got our pump seal. And the seal isn't going to look like a lot of the ones you guys have because you don't have a acrylic pump, and the standard seal won't work on this. And it allows us to abuse this pump a little bit like you're going to see us do. But it still has the same properties, principles that your guys' seals will have, and we'll go through some of those and discuss it. Also, while we're sitting here looking at the pump seal, we have some instrumentation on it. We have a pressure gauge on the seal chamber. So inside that seal chamber is where that's reading. That's right inside here, behind the impeller, okay? And we also have a temperature probe inside there. And that's just so we can see what we're actually doing inside there to the temperature of that seal. Okay, in front of that we have our rear cover on our pump. And then next we have our casing, or volute, and I'll use those words kind of interchangeably. And that's this clear acrylic part. Inside there, we've got our impeller in here, and that's a reverse vane impeller, a partially semi-open style, and that's something a lot of ANSI pumps will differ on, is what impeller is inside the pump. Either A, because this manufacturer thinks this style works better, or this manufacturer thinks this one works better, or also because to fit different conditions. For instance, this is a Flowserve pump. They have open face impellers or open vane impellers where the vanes face forward. They have reverse vane impellers where they face the back for different applications, and then they have low flow impellers for really low flow, higher head scenarios, so they can run on that end of the curve. And we'll get into some of that too, but just to say, different types of impellers come out of different pumps. Also, then we've got our suction of the pump here and our discharge here on top. We'll get into that a little bit more too, but then we've got some gauges and other equipment around this pump. First off, all this hosing and valving, those are seal flush plans. And we're not going to get into specifics now. We'll do that later when we start talking about the seal and showing what we do to this pump. Then on the suction and the discharge, we have pressure gauges, reading PSI. Then from there, we've got a suction valve over here that we're going to use to simulate problems when we start running this pump. And then we've got a discharge valve here. Last, we've got a flow meter up here on top of the pump. Okay, so that's pretty much all we're going to use as far as this pump. This is our tank, it's our supply. It'll simulate your guys' supply out in the field, whether it's from pipeline, from another pump, or from a tank like this here. Okay, so any questions on what we've got here with the actual pump physically?
And as this is running, obviously it's an acrylic see-through one, so y'all want to come up and look at it. We'll get some strobe lights on it to be able to, show the cavitation and all. So feel free to come up, stop at any time, ask questions.
Absolutely.
Look at it.
In that box should be a marker, a cardboard box.
Okay, so I'm going to talk through some pump curve basics and just what we're looking at here. And again, to make sure we're all using the same terminology, the same language, because there's a lot of those terminology stuff that gets lost in the pump world between guys like me and my company who are pump people and come from that world versus people in the field that are reading just off of gauges, off of meters, monitors, that kind of stuff that the language doesn't always correlate exactly. So this is your standard pump curve, and all of yours will either look like this or at least have all the same information that you get from your pump. And this is a published curve by Flowserve to match this specific pump. Okay? And all of your pumps in the field should also have a published curve or a curve that is specifically for your service. If you don't, you need to switch your pump company or give them a call and shake them or something, because they should be able to give this to you. If they don't, there's ways that we can build a curve for your pump in the field just by changing stuff, and we'll kind of get into that here in a little bit, and I'll show you how I built a curve for this pump specifically, and we'll talk about why I had to build one instead of using this as well. But more about the curve here. This up here is our power curve. Okay, it just shows if we're running at a specific spot on the curve, how much power is required. Sometimes on pump curves that'll be down here, sometimes it'll be within the rest of these pump curve lines, but there will always be a horsepower curve on your pumps. Next, on our big curve here, on the actual section where we're showing our hydraulic performance, across the top on the left side here, or going up and down on the left side, is our head measured in feet on this diagram, or this chart. And it's important to note, so we're all, again, looking at the same information. This is something really important when you guys are diagnosing problems or looking at pump performance in the field. I drew this little triangle in here to measure the delta head, okay? It's really important to understand. All pump curves are designed for differential head, okay? So that's the differential between what the pump has going on the suction and what it has on the discharge, okay? Also, while we're talking about what's going on over here, this is a pump term here, head, okay? A lot of us in the field, when we're out there working, we don't speak in that terminology. We prefer talking in what our gauges show and what our transmitters show, which is PSIG or bar if we're in somewhere metric, but either way, we all speak mostly in PSIG, okay? Head is a measure of the amount of weight of water that is in a column of water that is pushing down and putting pressure down on this suction or our discharge, or how much we have to overcome, okay? There's a way to translate that. There's a little formula where you can turn head into pressure or PSI, and it's different depending on what units of measure you're using. Such as if you get a pump that's from Europe, it might be in meters of water column as opposed to feet, you know, and that this conversion will change. This is the standard one we use, and I can get that to you guys if you want at a different time, but basically it's your head divided by 2.31 times your specific gravity. So it's going to change whether you're pumping water or condensate or salt water that has a heavier condensate because it's got a brine in it, or salt water, okay? So that's our head. That's on this left side here. Then from left to right on the bottom, we're going to have our flow, our capacity, increasing as we go to the right. This one is measured in gallons per minute, and that's what we're going to use just because that's what our meter is reading in. You guys, of course, probably switch a lot between gallons per minute, barrels per day, barrels per hour, a lot of that stuff. Again, there's conversions we can use for that, and if you guys don't have them, we're sure happy to provide them. Also, for most pumps, if your pump guy gives you this, and you say, well, this doesn't help me much because that's not what my instrumentation reads, most of these are all computer generated, and we can go back in and we can tell our computer that we need it in barrels per hour and we need it in PSIG, okay? And we can change that so it makes a more relevant curve for you guys when you're actually out there in the field looking at this stuff, okay? So, next we've got efficiency on this, and that's in percentage of efficiency. Next, in this little spot, we've got our NPSH in feet, okay? So then we've got a whole bunch of lines in here that can get a little confusing at times. We'll kind of walk through those. The actual pump curve, where the pump is actually operating, is going to be this one in the middle, and you can usually pick it out because there's three lines that will kind of be concentric. They'll all match each other. Whichever one's in the middle is going to be what this pump is rated for, okay? And the reason that there are those three lines that kind of match, those are all our pump curve. Our pump can operate anywhere within that top line and the bottom line, our minimum and our maximum. Yeah?
So are we just changing the impellers?
That's exactly correct. Changing or trimming your impellers. So what we've got here is a maximum is 6.25 inches, our minimum is 3.5 inches, and our rated is 5.3 inches. So if we have our maximum impeller in here, 6.25 inches, the pump will operate on this curve.
So once you have the unit in place, this is where you can operate with that pump, and you have to change the pump.
That's exactly right. That's exactly right. And there's other ways we can manipulate it, especially if it's on a VFD. Because a VFD has a very similar effect on your pump curve as trimming the impeller, because it changes the speed of the impeller, just like if you shrink the impeller, you change the speed of how fast the outside of that impeller is going. It has the same effect. And so on a VFD, if you slow it down, we move backwards towards the minimum of this curve. And if we speed it up, we go up towards the maximum of this curve, okay? And it's important to note, yeah, go for it.
Is the efficiency change per impeller? The efficiency curve?
That's a good question. I think it does, but I don't really know that. Yes, it will, because it changes the clearances in here, so it has to. So yeah, your efficiency will change. And again, this is something where if you need it, like you have a pump out in the field, and I've got this drawn in here, if you need to operate at this point, you call your pump guy and say, hey, I need an impeller that's about 6 inches. Can you send me one? They send you one. What you should also have them do at that point is redo your curve for you. So then you have a curve at 6 inches, and it'll show the rest of that information, because what also will change is your horsepower, okay? And this NPSH line will change. It will change the parameters of how that pump works. Some things will change a lot, some will change a little, but they're all going to change. So, if you need to change that, ask your pump guy, he'll get you a curve for it, make sure it suits, then order the impeller, and then you can do it ahead. Because if we want to operate there and we do change it, we might not have a high enough rated motor.
Okay, and I haven't seen an efficiency curve like this, so which axis? Oh, it's over there.
It's right here, efficiency, and it's in a percentage, and it's this line here. So
based
at
on
our
the corner of that triangle.
Yep, at our design point, you would rise or fall, depending on where you're at, to where that spot on the efficiency is, and then you slide over. So we're running at about 23, 24% efficiency on this one. Okay? Yeah.
And that's already represented in the horsepower.
Yep.
So
Yep. That is representative of what we're going to lose in horsepower. So when you slide up, it's going to show you what you actually need your horsepower rating to get to.
Okay.
And we're going to deep dive a little bit more into the efficiency, and I'll talk about why that is and what changes there. Okay? So let's stick with the pump curves here. We talked about our maximum, we talked about our minimum, we talked about our design. The triangle or X or pointer or different colored spot on your curve, that's where this is rated for. That's where your pump guy either designed it for or someone told that pump guy to design it for. That's where it's optimally designed to run. Other lines on here, we talked about the efficiency just now, okay? That just slides over and talks about the efficiency that this pump is converting this power into hydraulic power, okay? Because we can do a calculation on this board and show you if we're moving 50 gallons a minute at 30 feet of head, we can tell you how much hydraulic power that takes to actually produce. But that number only gets us so far because it doesn't take into account the efficiency of this pump, assuming clearances and its ability to convert that centrifugal motion into actual energy inside the pump or horsepower of that fluid to move. Okay? It also doesn't take into account the efficiency loss from your motor to your coupling to your shaft inside your power end here, or your seal drag, or any of those things that are stealing your horsepower. So that's all reflected in your efficiency here. Okay? And we'll kind of go through that. But the actual power to run what we're going to actually run at for these conditions is probably like 0.2, 0.25 horsepower. But because we're not very efficient on this pump, we have a 2 horsepower pump on here that runs all the way up to 1 horsepower for our typical needs. Okay?
That curve on the top is just your hydraulic horsepower, not the brake?
No, this is brake horsepower. This one here shows what you actually need. It does take into account your efficiency.
Sorry.
No problem. Ask all the questions. It gives me a chance to stop talking and take a drink. Okay? So, other stuff on this pump curve we need to look at. Really important line that we're going to talk about a lot today and simulate a lot of problems with is our NPSH line. That's net positive suction head is what that stands for. So our head, again, will translate into pressure, and we can read that right here is what we're trying to achieve is pressure here. And so that net positive is the amount of water column or pressure that we're putting from our suction down onto this pump, okay? And anything in this line will hurt us on our pressure. So you might be able to go to your tank and calculate the amount of weight that this water is going to push down on that pipe and equate to your pressure at the suction. But you need to remember that you have pressure loss in all of your valves, all your suction strainers, all of your 90s, all of your length of pipe as far as just friction loss. So when you're calculating that stuff, there's a lot to figure in to how to get that NPSH here in the suction. Okay? And we're going to talk about 2 different kinds of NPSH. Well, not 2 different kinds, but we're going to talk about it in 2 different ways. One is NPSH-A, which is available. How much NPSH we have available here at this tank to provide that pump. And that's how we're going to simulate some problems later, is we're going to cut that NPSH-A in here to where it doesn't meet what the pump needs. And that's another number we're going to talk about is the NPSH-R, or required for this pump to operate. So when available does not mean required, we run into problems. And we're going to simulate some of those problems with the pump here in a little bit. Something you're going to start seeing on all your pump curves moving forward is the pump gurus of the planet decided to get together and decided that NPSH-A and R weren't descriptive enough. And so now you'll see it written like this, NPSH-3. Okay? So that NPSH-3 number is a calculation of at what point when we lose NPSH do we lose 3% of our head. Okay, so if we have standard conditions running here, we're not changing anything inside the pump on how it's operating, but we start cutting back our suction head available, at what point do we lose, 3% of our pressure differential? That's where they calculate this line at, is that 3% loss. Historically, when we did A versus R, required versus available, they just drew that line at when you started damaging the pump. Now they do it on performance, okay? I thought the A versus R was a lot easier to explain than the 3% head loss, and that's how I'll usually talk about it, is your available versus what's required here, okay?
So as long as you're greater than the NPSH3, you're in a safe operating area?
Exactly suction, you have ample or enough above what's required, should be good. And as you approach that line, you'll start seeing a performance loss, and also at that time you'll start seeing problems inside the pump that'll cause you problems and damage the pump. Okay? The only other line on here that we're going to be concerned with, or that we're going to run into, is this line here. It's a vertical linear line that says MCSF. That's minimum continuous stable flow. Okay, so that's our minimum flow. And on your data sheet that comes with this pump, you'll see that written out as an actual number as opposed to a line, which will give you a very concrete number of where that's at. And so stable flow, that means basically when we start recirculating and having some problems inside this pump to where we're not getting a stable transfer of that energy of that centrifugal motion into the energy of moving that fluid, that's where we start running into this MCSF line. And again, we'll demonstrate kind of what happens inside the pump at that point. And usually that's measured at 10% of your best efficiency point. But again, how that's calculated isn't as important as what happens when you get there. Okay? Okay, so that's our pump curve. Any immediate questions on that? Okay, cool. Some consequences of us having this demonstration pump versus what you guys actually use in the field, cast iron pumps, stainless pumps, whatever, is we can't recreate the exact clearances of what this pump would be if it was a cast iron pump, nor could we abuse it like we're going to. Okay, it would destroy the pump. So our pump does not match the published curve. This published curve is for cast iron, so it's not going to have the same effect, the same performance. So this doesn't do us a lot of good at the moment. Okay, so we're going to pop it off and look at my chicken scratch handmade pump curve here. And this is another exercise where if we had more time, or if we ever came back and you guys wanted to do this again, we could show you guys how to create your own pump curve. Okay, it basically just starts with an empty blank draft paper or whatever, and you run your numbers up for pressure and run your numbers out for your flow, and then we just draw our own curve. Okay, and we'll explain how we get there, and we'll show you how changes on here will affect what's going on here, and how we follow that pump curve, and how this pump is a slave to this curve. Okay, because that's an important thing to remember if you're ever out troubleshooting your pumps, is it has to be doing what's on this curve, unless there's problems like your NPSH, where you're going to lose that 3% head, or if there's any damage inside the pump. But if it's properly operating, it has to do what this pump curve says, just by physics. So, that being said, again, we've got a figurative NPSH line drawn here. That's not actual because we don't have that calculated. I have a figurative efficiency line here. This is the actual pump curve based on what we see here and what we see at our pressures here. Assumed design point and an assumed minimum continuous flow point. So, that being said, we're going to turn this thing on and start showing you guys how this curve works and why we run on those places, and then we'll start simulating some problems. Cool? All right, let me make sure we're all tight and we're all good here. Should be. And there's something that when I set these pumps up, I like to kind of show, and usually it works, sometimes it doesn't. But a lot of things you guys will run into, or some problems you guys can run into, is vapor locked pumps. And right now, that's exactly what we've kind of got, unless it filled up, which it probably did, so it's not going to show. But if we just filled this pump up, there would be about a water level in here, and we turn it on, and it would just spin, and no water would go up. Okay, that is a true vapor lock problem. This one's kind of naturally priming, but a lot of your closed scenarios, you'll need to have a valve somewhere up here high to open up and let that fluid fill up this pump. Okay. Otherwise, it's just going to spin and not be able to transfer that energy into an actual movement, because it's just compressing the air inside the pump. It doesn't actually add pressure or add energy to the fluid. Okay? Like I said, unfortunately, we've already primed this pump just by it sitting here and kind of equalizing it. So, just make sure we're all open. And again, feel free to come up, take a look. As we abuse this thing and do different stuff, you're going to have to come look at it, because some of the things are kind of hard to see. But anyway, feel free to come up. is I'm tightening this discharge valve. It's going to act like a back pressure control or a constriction in the line to simulate putting back pressure on the pump to get us running where we want to on the curve. Okay. Alright. Check a few things. Make sure we're not leaking anywhere. Good. So, and where's that rag at? Because this valve will leak on it. Okay. So what we're doing right now is we're running at about 40 GPM here. So if we go over to 40 GPM on our curve to confirm that it's operating where it should be, we'll follow 40 GPM up and we'll run into this line or this point on our curve, draw that over. This is all in PSI on this side. We're about 16 PSI. So that's what we should be reading on here. And we have to remember, we're reading a differential across these two. So we can go in here and we're reading about half of a PSI of suction, okay? And that's important. And then up here we're reading about 15.5 PSI on our discharge. So add the difference between those two, we're getting 16 PSI, and we're operating where we're supposed to at 40 GPM. Okay? Now we're going to change this and confirm our other spots on the curve, okay? And this is how you draw your curve. Is when we hit that 40 and 16, we just draw an X. Okay?
I thought you said 15 and a half and half, so you subtract the half off.
No, you add it because it has to add to it. It has to do that work of pulling that
I
and
thought
then
that was
creating it.
Okay. I thought it's net.
It is net, but the difference between the two is 16 psi. The difference between negative half.
Oh, it was negative.
say
It was,
yeah.
it was
Yeah.
negative.
Yeah, sorry, negative half.
Yes.
I don't know if I said half a psi, but it's a negative half. Good? Okay, so we're going to increase ourselves up to 50 psi and confirm that point as well. So we're going to open it up. And we get about 50 psi, and you'll start hearing some different stuff going on. That's actually cavitation going across this valve as we close it and increase the velocity across it. So we'll kind of have to disregard that. But later we're going to hear it in different parts of the pump, and we'll want to be cognizant of that. It's going to actually show us some of the problems. So at 50 psi, we should be at, or 50 gallons per minute, we go up, we hit here, we should go across, and we hit about 13.5 psi. So on here we're reading about negative 1 psi, and on the discharge we're reading about 13.5 psi. So our curve actually isn't matching that. Okay, so we can adjust accordingly and erase and change.
You're not right.
What's that?
It's not right up there.
And of course we've got really, really accurate measurement here. Just a big deal hovering there, but we make do with what we can, right? So that actually brings us a little closer. We're at about 14 total differential. We said we were at 13.5, so for the demonstration that's probably close enough. So if we want to check some of these points up here, we just tighten up our discharge, constrict the discharge, cause more pressure to move through, and that'll actually move us up on the graph, and then we'll see what it does with the flow. As we tighten it, we move down on our flow up to about 30 gallons per minute or so. So 30 gallons per minute, we should be reading about 17.5 psi. So we're at 0 here, and we're at 15, 16, 17.5 psi. So we're good there. Okay? So that's just how you read the curve and how you draw your own if you need to. So we did 3 different points. When I drew this one, I actually did 1, 2, 3, 4, 6 different points, and then you just follow your line and you connect the dots there, and you've got your pump curve.
Aren't you just going to cavitate because of that vacuum?
To a point. There is a point of vacuum on this side where, yes, you will cavitate. But pulling a vacuum like 2 psi isn't probably going to do that. But we're going to put ourselves in a position where we're pulling a vacuum that does cause cavitation. That's going to be part of the demonstration we're going to do. So we're going to get there. Okay?
Wouldn't that be contingent on
especially down to, well, all the unconventional gas blades. It's a common problem across the board. We're seeing it out in West Texas, we have it down here, we have it in Ohio, because we're pulling out the really light liquids. You know, they have a very high vapor pressure, and it's a very tough problem for a lot of these pumps to handle. Okay, and that's exactly why, because your vapor pressure is a lot higher, and it's harder to handle. Okay,
Do you overcome that with your head and your tanks then?
that's the easiest way to do it,
Yeah.
but that's not always, you know, practical, because sometimes your pump has to be outside the burn or so far away from the tank, and that steals your NPSH. Sometimes you have, you can't keep enough level in the tank to do that, or, you know, different problems. But yeah, that's exactly what helps us to do that. Or like a truck unload, you can't increase the NPSH coming out of the truck unless you put it way up on top or put the pump way down in the hole, you know, which are solutions. But again, we'll kind of just, we'll demonstrate some problems with that and what that does inside the pump and why keeping it from those problems is a concern. So we're going to start the suction and simulate some problems there, and then move throughout the pump and cause some different problems on the discharge later. But we'll start here anyway. So again, we've got our NPSH line here. We're going to crank it up a little bit and run about 45 GPM. Close enough, just because that gets us a little bit higher NPSH. And then we're going to take our available and we're going to make it less than what's required here to operate it. Let's see what happens. Give me that light. Thank you. And you can start to already hear it happening. We're already, and if you look, we're already pulling a giant suction on our a giant vacuum on our suction. Okay, so we've already cut off a lot of that and started to cause problems. And so what that's doing again is it's decreasing here, and it's also choking out what our discharge pressure is, or our differential pressure is. So we know we're already past that NPSH line, and we can kind of try to figure out what's going on there. This is just a strobe light, by the way, that we just changed to the strobe to match the impeller. So it makes it look like it's staying still, makes it help to see what kind of problems we're running into. And this again is something you guys might want to come a little closer to see. But if you take a look here at the suction line, you can start to see cavitation bubbles happening. And I don't know if you guys can see it at the back, but basically it just looks like little tiny bubbles, or it looks like we're sucking glitter through the pipe here, okay? And if we turn that down and even cause more of it, those bubbles just get bigger and get more of it, okay? So it shows up here in the piping. And also, if we go towards the pump, you can actually see those bubbles at the eye of the impeller where they're coming in from the pipe, and they hit that low pressure point in the middle of the eye of the impeller, and they'll actually continue out towards the impellers. And they're out here on the vanes of our impellers as well. Just little tiny bubbles is what we're seeing. Okay? And so what that is we're creating that vacuum, and yeah, you can also see it usually on the seal as well, inside that seal chamber. See that? Okay? So again, what we've done is we have knocked down our available NPSH, which is causing our pump to continue to try to work at the same spot. Our pump still wants to create that 15, 16 PSI, okay? But we're making it work harder on the suction side to do so, as opposed to where it was working, which is on the discharge, okay? Which is a real problem if you guys are working in like a pipeline situation or a situation where you're filling up a tank that's 200 yards away, because you still need that much pressure on this side, and every bit you steal here makes it not able to function out on the other side, okay? So what we're actually doing and why those cavitation bubbles are happening and showing up is exactly what you guys are describing. As we decrease our pressure in this line, and we still have the same amount of velocity and fluid going through there, we create that vacuum and increase that vacuum to the point where we're breaking apart air out of that water, to where we're basically getting down below the vapor pressure of that water. and boiling it off inside the pump at a lower pressure. Okay? So what happens is those water bubbles and that air pockets will show up on the inside of this impeller. They'll catch the impeller and the centrifugal force, and they'll start moving out towards the positive pressure. And as they reach that positive pressure, whether it's on the impeller vanes or out here at the casing, usually in this scenario, it's towards the eye of the impeller, because we very quickly move out of that vacuum inside this pump and into a positive suction or positive pressure area. So as soon as they get out of that vacuum, those bubbles explode. Okay? That cavitation collapses in on itself. Okay? And what that does is it causes a very turbulent situation in there inside the pump, and actually will cause a lot of damage to your impellers and to your casing as well. Okay? So what that'll look like when we have a technician go out and you guys say, hey, we're having problems and you need to tear apart this pump and tell us what's wrong with it. He goes out there and he takes that pump apart. When he looks at that impeller, that's one thing he's going to look at is if we have our impeller, there's our eye, and it's got these vanes on it. A really good artist, by the way. When he'll look at the suction of that impeller, the eye of that impeller, and if it looks like there's a lot of corrosion, wear and tear on the eye of that impeller, he knows that's where the cavitation is happening, because that's where it'll wear out first. And what it'll start to look like is like that metal's been sandblasted, or it'll look like a sponge, like it's had little holes eaten out of it. And that's where that cavitation happens. Okay? So if we see a cavitation and wear inside of that impeller, we know it's from a similar problem, or at least that's where our cavitation is happening. And then we got to diagnose why that's happening at that point. Okay? So, you see where we're at here. Any questions on that immediately?
In the case where we do have light condensate, have you observed not cavitation but vapor locking while in operation from gas breakout? Like, say it's not collapsing again, and you eventually fill with enough vapor to lock it up. That's something you can observe.
Yeah. Commonly, no, but do we see it down here in this light condensate window type stuff? Yeah, we absolutely do. Yeah, I mean, we can agitate that enough to where it breaks out enough fluid to where it starts filling our discharge line or filling our casing and stopping us from being able to create that pressure.
But in that case, it's a different concern, right? It's wearing out burning up your seal as opposed to running your.
Correct. And we'll kind of get into that. And one thing that, well, we can talk about it now, I guess. One thing that happens when you create that vacuum in the eye of your impeller is it's not only pulling the vacuum here, it's trying to pull that in from everywhere it can, or rush in anywhere it can. And as you know, probably your mechanical seals, they all have a rotary face and a stationary face. And those two faces create your seal between your ambient outside your pump and what's inside the pump and the pressure inside it. And those are all mostly product lubricated. So for you guys, they'll be lubricated by your crude or your condensate or your salt water or whatever. And they will run on a thin film in between those two. And that's what creates a seal and keeps them from overheating. And that seal chamber back here, moving fluid through that is what clears solids out and that stuff, and it also cools that seal. Okay? So one of the problems of creating that vacuum, one way or the other, is that the pump will try to pull air in through your mechanical seal, because that pressure drop is also seen back there. And we can turn it on and show you on this gauge here that negative hits there as well. And again, as soon as we pull air through there, we've broken our seal where we have that thin layer of the product that lubricates that. We've lost our lubrication, and either the seal faces will bounce off each other and cause a lot of damage on the seals, crack them, break them, chip them, whatever, or they will just heat up to the point where they'll cook and bake and not be able to do their job anymore and seal the ambient from the inside of the pump. So yeah, it manifests itself there in seal problems as well. Okay? Any other questions on that before we move to kind of the next or another problem with the pumps? Okay, cool. Just don't want to run this too loud while we're all trying to talk over each other and talk over the pump. Okay. So, just to demonstrate what you were just talking about, we can go back to our suction cavitation. Oh yeah. So we're pulling a suction here, and we moved from before we turned on our NPSH, we were running at about 5 or 8 psi positive on our seal chamber. Now we are running at about a negative 7 or 8 psi on our seal chamber. Okay, so that's again putting yourself in danger of pulling air or vapor in through those seal faces. Okay. Okay. Now we're going to talk about, go back to the curve real quick and talk about some common problems or areas of concern on here, then simulate them again on this. So we talked about that efficiency curve on what you guys have, and once you start falling off of that in either direction, you start getting into problems. You know, guys will talk about not running off the curve. Hey, don't run off the curve. That's all well and good. Yeah, you don't want to be running out here off your curve. But if you start running toward the edge of your curve, you're still going to be causing problems for your performance and for the lifespan of the pump. Okay, we're going to talk about some of those. And how they figure that is the pump guys will get together and they'll say, you should be running between 85% and 115% of your best efficiency point. Okay? And off of that, you start seeing problems with your pump. And that's just a number, that's an API number actually, not an ANSI number. So if you guys are looking at API 620 pumps and what's required of those, that's one of the requirements that they try to put on those pumps as a best practice for operation. And it translates here too. So what they talk about is here's your best efficiency point, the point at which your efficiency curve is the highest. As we fall off of that, let's say we fall off to 15% on this side, which would be 85% to the left. We run into this line here, and I'm going to show you what that line is. On this side, we run into 115% on the right side, increasing that direction. So there's a window of that efficiency that we like to run in. That's where the pump should run. It's happy it runs there. It'll run there forever. Okay. But once we start escaping that on either side, we run into some different problems. We're going to talk about those. The first one we're going to get into is this side and what happens out here. In this area, most of us pump guys will call that run out or going to the right of the curve. So how that happens is obviously we need to increase our pressure and increase our flow to get there to simulate our pump. To do that, we have to drop our pressure. Okay, so we're going to move down on the curve and out to the right. Okay, so we're going to do that by opening up our discharge valve here. And we'll see we immediately start going. And there's something I want you to look at while we're doing this because it's one of the problems you often run into out here. Remember our horsepower line from the other curve. Our horsepower line goes this direction. It goes up as we go to the right. And that's sometimes counterintuitive because as we go to the right, we lose less pressure. And a lot of times you'll think, well, more pressure, I need more horsepower, right? Not with the centrifugal pump because what's really doing the work is your flow. Moving that mass of volume is what actually does the work or horsepower, okay? So as we move to the right, even though we're decreasing pressure, we're increasing the amount of horsepower required because it takes more effort and more work to move that volume, okay? So we've got our horsepower monitor here. We're at 1.1. I'm going to crank it back down to where we're like 20 gallons a minute, so we're way back here on the curve. And so we are at a 0.9 horsepower on there. And so we're going to work our way out here, and you guys can watch what happens there on our horsepower monitor. So as we keep moving up, it just keeps going up and keeps going up. We're at 1.3, at 70 GPM. We can't get too much beyond that. We run out of valve. But so we're at about 70 GPM there and about 1.3 horsepower. So as you guys can see, as we move out there on that end of the curve, we increase our horsepower. And that's where a lot of problems happen. If we get called and say, hey, our motor keeps tripping the breaker and we're running out of horsepower or whatever, why are we doing that? Well, the first cause is you're probably running out here and your curve too far. Okay? So, again, common problem you guys might run into. Okay, so what happens out here at run out? Which, by the way, we're running at 75 GPM. We go to our pump curve, we're not even on the curve anymore. We're out here in La La land. and we are running at a negative 8 psi here and about a 4 psi there. So we're running at a really low pressure on the discharge and the suction over here. Okay, so problems that we have at this point is we've increased the velocity of that fluid moving through there just because there's more of it going through the same constricted space. Okay, and so what we'll see is, this one's a little tough to see, but you have to kind of come close if you guys want to see it. But out here at the tips of our impellers, you'll start to see a little flex. And that's the same thing that we were showing earlier, it's just in a different spot in the pump. And this just basically looks like we're pumping glitter, because it's a lot smaller bubbles, but it's the same deal. I'll do this so you can see there. There it is. Same deal. I don't know if you can see it as well from the backside, but it also happens at the seal chamber, which you can see there. And so what we're doing is, by increasing that volume so much, we have increased the velocity of that fluid around the casing of our pump and around the tips of our impeller. So by increasing that velocity, there's small pockets of low pressure where we create those cavitation bubbles again. And we're actually doing, and creating those same cavitation bubbles, and as soon as they hit the positive pressure out here, or the positive pressure right outside the casing, they collapse again and cause that same problem. So common problems when we take a pump apart that's been having this problem, what we see is the casing will be wearing out prematurely, and you'll see that same sponge or sandblasted look around the outside of the casing. And you'll also see it at the tips of your impellers, because that's where this cavitation has happened, and we showed right here. Okay. Other problems are you're often running into the service factor of your motor, wearing out your motor, other things. It also puts more shaft deflection on your pump, causing premature bearing failure inside your pump. Okay. So a lot of bad things happen when you're running out here at run out. That's called run out, like you said. And that's kind of just the pump terminology for us. Okay? I'm not running up against time barriers, am I?
Yeah, you're fine. 3 minutes.
3 minutes, all right. Okay, we're going to go to this side of the pump real quick, show you guys what happens there. Us pump guys are going to call that backing up on the curve or running left of curve. Okay? We do that again. Increase the pressure, and we run back on the curve. Do that by pinching off here. So we're at about 10 or less GPM there, so we're all the way back to 10 right here, about 19 psi, 20 there. So what happens here is a little different than what's going on here. A similar thing is seen inside the pump as far as the cavitation happens out of the impellers, but it's for a different reason. Right here we're running up to we're running into the minimum continuous flow line, minimum continuous stable flow, and it's because our pump cannot impart enough energy to overcome the pressure we put on it. This could be from a packed pipeline, it could be from an obstruction in the line, it could be because of the change in your fluid, whatever it might be. But the pump is starting to have an inability to move this fluid out of the pump because of that pressure. So that fluid has to do something. It's still there. So what it does is it starts recirculating inside that pump. Okay? And what that is, sometimes they'll call it vortexing. But basically what it is you're getting little vortexes on the outside of the pump around this casing. And so if we turn our light on again, you start to see that we're pumping that glitter again out towards the outside of these impellers. And again, this pump is kind of hard to make this show, but it will do it. Yeah, you can see it there. Real quick, I want to make sure you guys see this before we go. So things that happen when we do all these bad things to these pumps is it shows up in different areas of the pump. One is inside your pump here. You guys have heard the vibration and different things that's going on in here. That's all vibration that's being translated into these bearings inside this pump power end. Okay, decreasing your bearing life. Okay, so that's a common problem that we run into with these. Another is your seal performance and your seal life. What we haven't looked at here is our seal temperature. Right now we're running at 101 degrees Fahrenheit. Okay, that's a problem, and we're researching. Some of that's because we are pulling a suction there. We're cavitating inside that seal chamber. Okay, and then the other is recirculation inside the pump. Just heats everything up. So what these are, I wanted to get these before you guys leave. We have two different seal flush plans that are on here. One is a plan 11, is what we call that. And that translates across all the pump world. Everybody knows what that means in the pump world. And it comes from your discharge, the high pressure end, which right now is 18 psi, and it goes to the low seal pressure here, which is 8 psi. So this is going to overcome that and push fluid that direction. Okay? And this one is called a plan 13. Okay? Plan 13 goes from the high pressure in the seal chamber, which is 8 psi, and pushes fluid to the suction, which is over here at half a psi. So it goes the opposite direction. Okay? And there's benefits to both of them. They're both good because they both cause a decrease in your temperature. Okay? First one we're going to do is this plan 13. When we open it up, we're at 102 degrees. Okay? When we open that valve up, that pressure should start going from our seal to suction. So what we're seeing, first off, we dropped a few psi on our suction chamber, which is always good, running the lower pressure in there. It makes your seal not work as hard. But we've already dropped 3 or 4 psi, or 3 or 4 degrees on our seal chamber. I'm going to close it now because I don't want to totally cool that thing down. But again, a cooler running seal, always going to be better, okay? Unless you get obviously too extremes. So that's the plan 13. And a plan 11, you're going to see a similar effect. We're going to turn that on here, so we're running at 100 degrees. We open that up. And so again, we're going from the high pressure here and going back into the seal chamber there. And what you'll see is this isn't quite as efficient at cooling the seal. Again, because we're moving, imparting all this energy into this fluid through that pump, and it actually heats up that fluid as it goes through the pump. And so this is going to be warmer here than it is here at the suction. So it's not going to be as efficient at cooling your pump. But we're slowly, no, we're not dropping yet. Did I open it? Did I close that one? Maybe we heated up the whole system too much. And it will start dropping. We'll keep an eye on it here. But the other benefit to the Plan 11 that we use a lot in our industry is because it creates a positive pressure inside that seal chamber. And that seal chamber, that shaft goes through, hits your seals on your faces, and then there's an open seal chamber where there's actually fluid circulating. Okay? And that's used to cool. Yeah. I would be. Because what it does is, I mean, A, it gets debris out of that seal chamber, whether it's paraffin, frac sand, who knows what else. It actually pushes that into the pump and up down your discharge lane, okay? Another thing it does is it does cool that pump, or that seal. But it also keeps additional stuff from coming from your suction into that seal chamber. So it creates that positive pressure. So we're running at about 9 or 10 psi on there, which versus our suction, which is at 0. Okay? So that's your Plan 11. And we do recommend running those. In fact, whenever we send a LAC unit down or a centrifugal pump, we will add it on whether the customer wanted it or not, because we think it'll help that seal last longer and keep a better lifespan.
So how often will you flush them?
No, we leave them open.
You just leave them open?
Yep, leave them wide open, because you never know when frac sand is going to enter the pump, get inside there, or you never know when you might need to cool that pump.
So you leave both of those open, the 13 and 11,
Actually,
or just the 11?
We'll usually only run a Plan 11 because
Okay.
it increases that pump, that pressure inside there and keeps them cleaner longer. Okay, so we'll usually just run a Plan 11, but a Plan 13 is also very effective at doing a similar process.
So is it kind of a slipstream, basically?
Yeah,
I mean,
exactly right.
But it's small enough it won't affect your efficiency currently.
Correct. I mean, it will, but it's not enough where you'll actually be able to measure it here. So, and I know we're out of time and the other group's out there waiting, so I don't want to keep them waiting. But guys, feel free to grab Chris's card. I left mine in the truck. I'm Tim Evans again out of San Antonio. Chris is our manager out of there. You can feel free to bug him. Again, as far as pumps go, we're more than happy to take a look at your guys' pump issues, pump problems, do any service on them that you guys might need, even just help troubleshoot. We're happy to do some of this on practical problems that you guys are running out there. Okay? Cool.
Good seeing you again.
Yeah. Tree?
When you're running under the minimum flow, does it just keep spinning until you have enough volume to restore it?
Or when you're running behind the minimum continuous flow. No, it's gonna still move fluid. It's just gonna recycle more of it in here.
Yeah, so it's just
Yep, yep. And it will move the fluid, just not all of it.
Yeah, you know how to find.
Yeah, someone told me, and I guess that was my prior experience, is from this, you immediately sledge up. Is that necessary?
Necessary? No, but you're gonna see an increased, it's good practice.
Oh yeah, I guess the good practice that
Here's some
they relayed to me was use
We've actually finally put together a deal
use
that's kind
90
of all of
on
our
the
products.
discharge and use citrus producer on that.
You always want an
All of
eccentric
it on
producer
one
on here,
thing.
you don't wanna cause a vortex there.
Mhm.
So that helps do that.
Thanks
The
for
more
having
critical
us.
one
Yeah,
is
I
you
might
want
not
to
stick around
swedge
for the
up
whole
on your
thing,
suction,
since
is a more
I'm gonna
critical
just
than
get
the
my first
discharge.
20 minutes.
And that's because
You
it
catch the
gives
front
an
end of it.
extra volume here
Perfect.
to increase that NPSH going into the pump.
Yeah, it was always like one pint size larger here and then one pint size larger
Yeah.
here. Was recommended. And then what about, well, no, that's pretty much it. What do you think about air limits?
There's good ones and bad ones out there, but they're good. You definitely want them.
Good practice to install
Good
those on the
practice to have.
discharge.
Yeah, absolutely.
What did you just ask about?
Air eliminators for yourself.
Okay. Okay. Is this the last one?
I
Last
have a lot
group?
going on.
Well,